For this video, we'll look at deriving the kinematic model for a differential drive robot. So, in terms of our robot, we have our differential drive robot here. This is our robot. It's differential drive, so we're going to have two drive wheels. We'll call this wheel 1, and we'll call this wheel 2. It is important to define which is your wheel 1 and which is wheel 2, and which way you count as positive rotation. Okay, so defining this as wheel 1 here, wheel 2 is this one, and positive rotation in that direction. We've got our coordinate frame for our robot. So our x coordinate frame is in the forward direction, and then the y is perpendicular to that. And the robot is going to have a certain velocity, v of t, and a certain angular velocity, omega of t. So the factors that affect them velocities are the wheel speeds. So we've got a wheel speed, Phi1 and Phi2. So depending on how fast them wheels spin, it's going to affect how fast the robot moves. Also, the radius of the wheels are, so the larger the wheels for a given angular velocity, the faster it's going to go. And then the distance between the wheels, L. So, the distance between the wheels is classed as 2L. So we've defined L as the point from the origin of the robot reference frame to the wheel. So the half distance is L, or the distance between the wheels is 2L. And the L comes into the equation when the robot starts to turn. So L will be a factor in its turning velocity. So them four parameters affect the robot velocity in the robot frame of reference. If we want to then transform that into the global frame of reference, we need to know the rotation angle theta between the two frames of reference. So these 5 factors, or these 5 parameters, will come into our derivation for the kinematic model. So what we'll do is consider each component of velocity separately. So firstly, we'll consider the x component of velocity. So what we do, might be easy if I draw this on paint, is we have a wheel. So take our wheel. This is rotating at an angular velocity of theta dot. So it's rotating around, and it's got a radius of that of r. So it's got a radius r, rotating at an angle of phi dot, and this is going to make it move at a velocity. So if it's rotating that way, it'll move at a velocity v, which will be r phi dot. So the speed of that wheel is dependent on its velocity and its radius and its angular velocity. So if we now take our robot, so we'll just quickly sketch our robot. We've got a wheel here, omnidirectional wheel here. We'll just draw this line in, so this is our reference point P. Now what we'll do is consider one wheel moving at a time and the other wheel stationary. So if one wheel is stationary, we'll say this point is fixed here. So we translate this down. This wheel is stationary. This is our axle. And then this wheel here is moving forward. So it's spinning. This wheel is rotating at angular velocity of phi dot. We'll call it wheel 1. So it's rotating at angular velocity of phi dot 1. And this gives it a certain velocity, v1. If we take our reference point of our robot, P, it's halfway between the wheels. If this wheel is moving at velocity v1 and this point is stationary, then if I just complete this, it means point P here is moving at a velocity, so the velocity of point P is going to be a half v1. So the velocity of point P due to wheel 1 moving and wheel 2 being stationary is half the velocity of wheel 1. So we can say the velocity of point P with wheel 1 moving and wheel 2 being stationary is given by this value here, a half r psi 1 dot. You can do similarly with wheel 2 and say wheel 1 is stationary. So if wheel 1 is stationary and wheel 2 is moving at r psi 2 dot, then point P is going to be moving at a velocity of r psi 2 dot over 2. So if wheel 2 is stationary and wheel 1's moving, it's got this much velocity at the center point. If on the other hand wheel 2 is moving and wheel 1 is stationary, it's going to have a velocity of this. If both wheels are moving, we add both components together and we can say that the velocity of the robot with respect to both wheels moving is given by this term here. So the x velocity is dependent on the rotational speeds of the wheels and the radius by this relationship. If we consider the y component of velocity, a differential drive robot cannot move sideways, so it's got 2 standard wheels, and standard wheels don't move, or they don't slip sideways. So we can say the y velocity of the robot is going to be 0. And in terms of our angular velocity, so again, if I go back to paint, we can do the same argument again and say I can say wheel 1 is stationary, wheel 2 here is moving at a velocity of v1, which is r psi 1 dot. We've got reference point P here. Point P doesn't really matter in this case because what we're doing is we're working out the angular velocity. So we're working out how fast this is rotating. And we'll do it about this point here. This is a stationary point, so this is where it'll be rotating about. So this is L, this is L. So our distance is 2L. Our velocity at this point is r psi dot. So we've got V equals distance x omega. So our angular velocity omega is V over x, where in this case V is r psi 1 dot and our x is our distance, which is 2L. So the rotation caused by this point being stationary, or this wheel being stationary and this point moving, is given by this value here. And this is the contribution due to wheel 1 moving. So let me go on. If we do similarly, but we keep wheel 1 fixed and wheel 2 moving, then it's now rotating about this point, so it's got an angular velocity in this direction. A similar argument, so omega 2 would be the velocity of wheel 2 over x, which is r psi 2 over 2L. Difference in this case is now we've got anti-clockwise rotation. So as I said, it was important to define which way you class as positive rotation. We've classed positive rotation as anti-clockwise, and therefore, because this is in the different direction, this will be minus. So our total angular velocity of the robot is this term, and this term combined. So we've got this due from one wheel, this due to the other wheel, and therefore combining these two to give us our total rotation of the robot gives us this term here. So combining them all together, we've got the speed of the robot is given by the x velocity, x dot, our y velocity, which is y dot, and our angular velocity, omega, or what we're saying is we're classing that as theta dot. So our x dot, y dot, theta dot is given by our three terms here. If we want to represent that in terms of our global frame, we need our transformation matrix to translate that velocity into the global velocity. So as a very quick example, we've got, I've got these as dimensionless, so you can put your own units in. So we can say, for example, 1 centimeter here, so we're working in centimeters. For example, you've got a wheel radius of 1 centimeter and an axle half length of 1 centimeter, and the robot is angled with the global frame at 90 degrees. Then given you've got a wheel velocity for wheel 1 of 4 radians per second and wheel 2 of 2 radians per second, what is the velocity of the robot in the global frame? So we've got our equation from our previous video. The global velocity is our inverse transformation matrix times by the velocity of the robot in its frame of reference. Our transformation matrix has got our pi over 2, our 90 degree angle in there. Our robot velocity is defined by our equation we've just defined here. So we put in values for r, put in our values for our rotational velocities of the wheels, put in our axle half length L, put the values in, work it out, you get 301. Multiply it out, so this is the velocity in the robot frame of reference, and then to get it in the global frame of reference, use our transformation matrix, and therefore for them wheel velocities, that is giving us a global velocity of 0 in the x direction, 3, I said we're working in centimeters, so 3 centimeters per second in the y direction, and 1 radian per second anti-clockwise rotation. So that is what's called the forward kinematic model, and given the wheel speeds, what is our velocity? The inverse or the reverse kinematic model is if we want a velocity, so say we define a velocity, we want the robot to go 3 meters per second forward. What wheel speeds do we need to drive that at? So it's a fairly simple case of just using the formula again. So given a global velocity, use our transformation matrix to give us our robot velocity, and we know our robot velocity is defined by this equation, and then we can just put the values in and solve for this. So again, another quick example. Again, we've got this 90 degree rotation between our frames of reference. We've got r is a quarter. So in this case, we'll say we're working in meters in this case. So r is 25 centimeters radius. Axle half length is half a meter, 50 centimeters. We've got we've got a global velocity we want of 0 in the x direction, 3 meters per second in the y direction, and an angular velocity of 1 radian per second going anti-clockwise. So plug it into our formula. We translating our global velocity towards our robot velocity, and then our robot velocity is then given by our corresponding equations. So if we put global velocity in here, transform this, And this then gives us, so this is our epsilon I dot. This is our transformation matrix between global frame and robot frame. So then this gives us our velocity of the robot in the robot frame of reference. So we need an x velocity in the robot frame of reference of 3 meters per second, nothing in the y direction, and 1 radian per second rotation. And that corresponds to our equations. So we put our values in for radius, our axial half length, we get phi1 dot over 8. So we're getting phi1 dot over 8 plus phi2 dot over 8. So this term here equals this term, so that equals 3. We've got 0 equals 0, so again, just to check that our calculations have been correct. And then we've got this term here, so we get phi1 dot over 4 minus phi2 dot over 4, and that has to equal 1. So a pair of simultaneous equations, we can solve for that, and if we solve, we'll find we get phi1 as 14 radians per second and phi2 as 10 radians per second. So given we want a certain global velocity, we can work out what wheel speeds we need to accomplish this. So that was for our differential drive robot, and that's the simplest kinematic model. So what we're going to do in our next video is look at a general case robot, so that it could be any configuration, and derive the kinematic model for that. And then given that, we'll then apply that to a differential drive robot, so hopefully we'll come out with the same equations, and also an omnidirectional robot.